What we're going to do is we're going to learn some new methods for balancing reactions, in particular for balancing redox reactions. Because in a redox reaction, we have transfer of electrons from one entity to another. And so you have to track that. And this is why we wanted to spend some time being able to assign oxidation numbers. Now we have two methods for balancing redox reactions. Okay? And so our first method is balancing using oxidation numbers. So in this method, okay, the first thing we want to do when we're using our oxidation number method is we assign oxidation numbers to all of the entities. So everything gets an oxidation number. So we would go through and we would assign oxidation numbers to all of the things. So start off with the easy one, oxygen, which is always -2. Okay, monovalent metals by themselves, their oxidation number is equal to their charge. And then we can use the sum of the oxidation numbers being equal to the charge to get our oxidation numbers for the other entities. Okay? And so now, once we've assigned all of our oxidation numbers, our next thing is to identify the entities that had their oxidation numbers change. Okay? And so here, we can see that manganese's oxidation number went from +7 to +2. Since its oxidation number is less positive, more negative, it gained electrons, and so it underwent reduction. And we can see that my sulfur's oxidation number got more positive, so therefore it underwent oxidation. Okay? So once we identify our entities that underwent change, our next step is to determine the number of electrons that were transferred per atom. So because we had a change of 5 for manganese, it gained 5 electrons. And since we had a change of 0.5 for my sulfur, it lost half an electron, each sulfur. Then what we can do is we can take into account the fact that they're part of a compound, and so we would multiply our change per atom by the subscript. Okay, and so here we'll get 5 electrons gained for each permanganate. Whereas here, because we have a subscript of 2, I'm going to multiply this by 2 because there's 2 sulfurs in S2O32-, and each one lost an electron. So it's 1 electron lost for this polyatomic ion. Next, what we're going to do is we're going to multiply them by coefficients so that my number of electrons lost and gained are equal, because the electrons lost by one have to be gained by the other. And so in this case, if I multiply my second entity by 5, then if each one of these lose 1 electron, 5 of them will lose 5 electrons that can be gained by this. So then I'll multiply that by 1. Okay, and so I can therefore take these numbers and put them as my coefficients in my equation. Now I'm going to balance all of my non-oxygen, non-hydrogen based on this 1 and 5. Okay, so we're going to balance everything but oxygen and hydrogen. So therefore, I'm going to place 1 for my manganese, and I'm going to place a 2.5 for my sulfur. Now, having a fraction in it will make it difficult to solve, so what we can do is we can multiply everything by 2, and it will get rid of my fraction. So now, at this point, everything except for oxygen and hydrogen are balanced. So now what I'll do is I'll balance my oxygens. So to balance my oxygens, what I'll do is I'll add one water for each missing oxygen. So if we look on each in my balanced equation, I have 50 oxygens in my reactants, and I only have 30 in my products. So I'm short 20 oxygens. So therefore, I'm going to add 20 waters. Now, I have hydrogen on one side of my equation, but none on the other. And so therefore, for each hydrogen missing, I'm going to add 1 proton. Okay? So I'm going to add 40 protons. So now this gives me my balanced equation. And I'll just rewrite it. Okay, let's take a look at another example. But in this case, what we're going to do is we'll just change the conditions to basic rather than acidic. But everything we've done is, for the first example, is the same. We'll just have an added step. So the first thing we're going to do is assign our oxidation numbers to everything. So I can assign it to the hydrogen, to the oxygen, to the nitrogen, to the sulfurs, and finally to the copper. Okay. Then what we're going to do is we're going to identify who has a change in oxidation numbers, and because copper gets less positive, it underwent reduction, and sulfur got more positive, it undergoes oxidation. Okay, once we identify our change in oxidation numbers, then we're going to determine our change per atom. Okay, and I went from a +2 to 0, so I gained 2. Went from a +3 to a +4, so I lost 1. And then I'm going to determine a change per ion or compound. Okay, and so I gain, since this compound has 1 copper and it each gained 2, it's 2 coppers for the compound. Since this compound has 2 sulfurs and they each lost 1, it's 2 lost for this compound. Next, I'm going to determine my multiplier, since they each gained and lost 1. And then I'm going to now balance my non-oxygen, non-hydrogen, based on there being a 1 here and a 1 here. So now, because there's 2 sulfurs in this compound, I'd have a 2 here. And because I'm balancing this compound non-hydrogen, I have 4 nitrogens. Now I'm going to balance my oxygen and hydrogen. So I'm going to add 1 oxygen for 1 water for each missing oxygen. So I have 6 oxygens over here, with only 4 there, so I add my 2 waters. And then I'm going to add 1 hydrogen proton for each missing hydrogen atom. And so I have 16 over here, and I only have 4 here, so I had 4 protons. Now, this would be my balanced equation, except we set out at the beginning that it's basic conditions. And we know that if I have hydroxide and protons, they're going to react for water, to form water. So therefore, for each proton, I'm going to add 1 hydroxide. But because this reaction is already balanced, I'm going to add 1 hydroxide to both sides, so that I maintain my balancing. Okay. Now we know that this proton and these 4 hydroxides are going to come together and they're going to form water. And now I have waters on both sides of my reaction, so I can reduce my waters. Okay. And then finally I can just rewrite my equation.